Okay, we wait a little bit more. Hopefully more students should be coming in. Right. Guess maybe we should start by giving a revision on what we have learned on Tuesday, on Monday. We have been staying on the lecture notes set number 3, and in particular, we were discussing about the case of the sound wave in the last 2 lessons. For the sound wave, the main topics that we discussed was the Doppler effect, which is a change in the observed frequency of the sound, as we introduced, when there is a relative motion between the source and the observer. Of course, the Doppler effect can also occur in other types of waves, and sound is introduced as a particular situation for the Doppler effect because that is something you could easily hear. We have shown it in the YouTube videos how a moving ambulance, for example, can generate a change in the observed frequency of the horns or of the siren. The equations that we use depends on whether it is the source or the receiver moving. So the situations are slightly different. For the case of the source moving, it is a change of the apparent frequency due to the change of the wavelength. When the source is moving, it compresses or enlarges the wavelength, and therefore the observed frequency by the observer would be changed. On the other hand, if it is the observer moving, it is a change of the wavelength due to the change in the relative speed between the sound and the observer. Normally, you have the stationary observer and the speed of the sound relative to the observer is a constant. But when the observer is actually moving, then the speed of the sound relative to the observer is not the constant that we normally quote. It changes according to the speed of the observer. So there would be a change in the relative speed and therefore a change in the observed frequency by the observer. Equations, which is listed here, depends on whether the observer or the source is moving towards each other or away from each other. So given the equation, you may have to make the judgment on what signs to use, for example. And the explanations have been given in the lecture notes. And we have worked on a number of tutorial questions in the class on Monday. The shock wave was introduced as a qualitative introduction, just a very special phenomenon when the speed of the sound is actually lower than the speed of the source. And in that case, you would have the phenomenon called a sonic boom, where all the wave fronts are compressed together and all the sound comes to the receiver at the same time. So this is the case of the sonic boom. And today we will try to finish the lecture notes number 3 by covering the topic of the superposition and the standing wave. Once again, it is not a phenomenon that occurs only in the sound. It occurs definitely in light. In particular, in the physics 2 courses, you will be learning about the interference of the light, and you will see the superposition. But here, it will be just a starting introduction, and we use sound. Once again, that is something quite easy to observe. And actually, we are not confining ourselves to sound. We would be talking about standing wave, for example, in a string as well. So the idea of the chapter 18 would be the following. Firstly, we will try to explain the observation of the standing wave and the resonance effect. And secondly, we would describe a very interesting phenomenon called beats. It occurs when you have the superposition of the sound, superposition of two sound waves that have slightly different frequencies. The effect is it would generate a periodic variation of the sound intensity due to the difference in the frequency of the two sources. So we would have a quick observation of the phenomenon and try to build up some equations from that. Firstly, in order to talk about the standing wave and the beats, we actually should introduce the concept of the superposition principle. Now, I believe that this is something you have learned before, but just as a quick summary, here is the verbal descriptions of the superposition principle. It is the description for the scenario when you have two or more traveling sound waves or traveling waves in general, traveling waves that are meeting with one another. The case is like this. You have two waves. For example, one is traveling from left to right, and the other one is traveling from the right to left. So something like that. So this is t equals to 0. And then you may have later the two waves hitting on one another. T equals to, say, T1. Now, what would happen is that as an outside observer, you would no longer be seeing two separate waves. But say if it is a single string, you set the oscillation on the two ends of the string, the two pulses would be traveling towards one another. At some point in the time, they would start to meet. What you will see is that the two pulses start to add with one another, and you would be observing the final pattern, which is actually the sum of the amplitudes due to each individual waves. So for example, at a certain time, the displacement due to the wave traveling from left to right is x1. And at the same time, it would be x2. Then when they meet together, the resultant would just be the sum of the individual amplitudes. So if you have the two waves that are traveling towards one another, then as the description suggests, the resultant value of the wave function or the resultant magnitude of the displacement at any point is just the algebraic sum of the values of wave functions of individual waves. So the idea simply is that at any location, the final amplitude or the final displacement is due to the sum of individual displacements. If they are displacing in the same direction, for example, if they are both moving upward, then you would, of course, add them together and generate a much larger amplitude. If they are in opposite sense, one is moving up and one is moving down, then they may cancel partially or completely. So this would be the scenario of destructive interference if you have learned it before. But the fundamental principle is the superposition principle. So superposition principle tells us that when the two waves meet, resultant of the wave at any point is due to the algebraic sum of the amplitudes of individual waves. So that is the idea in general. And how is it going to affect us in chapter 18 of the lecture notes? Now, actually, although the topic of the chapter 18 is related to standing wave, it is actually somehow a misleading term, a misleading way of saying the thing, because a standing wave is actually a result of traveling waves. Why is it like this? Now, I will show you a simulation, and you would start to see what is the effect of traveling waves that are moving towards one another. So at here, let us take a look at the screen. Okay. So here, I believe that I'm showing the screen. Let me just check. Okay, I should be showing the screen. Now, this is a simulation on the internet, and it demonstrates how you generate a standing wave, as the name would suggest. But as we will see, it is not really a truly standing wave that does not move at all. It actually is involving traveling waves. It involves traveling waves. So how it works out, let us take a look. At the beginning, there's nothing. So you can set various parameters. For example, it can be a reflection from a fixed end. So the idea is we are sending a wave from the left to the right. And during that, if we set the send away from the left to the right, of course, it would hit on the end on the right-hand side. So we set it, for example, as a fixed end. If it is a positive displacement at the beginning, when it hit the fixed end, according to what we learned, it will send us back a negative displacement. That is the idea. So let us start. And we start with a slow motion. Okay, it's too slow. Let us make it faster. So nothing really impressive is happening. It is just the wave traveling from left to right. Just want to say that it is a red wave traveling from left to right. Okay, now it is about time. So it hits on the right-hand side. Notice that the red wave is for left to right. The blue wave, on the other hand, is from the right to left. Notice that it is hitting on a fixed end. Therefore, the wave is displaced downwards. That is the idea. Now, there are several things you could see in this simulation. First is the incident wave. And second, it is the reflected wave. Finally, it is the sum of the two waves. The sum of the two waves is shown in black. The incident wave is in red, and the reflected wave is in blue. So let's resume. What can we see that here? The black, as we mentioned, it is the resultant wave. As the time develops, we could see that now, as a whole, it seems that the wave is not moving to the right or to the left. But if you take away the resultant wave and put back the incident wave and the reflected wave, they are actually still traveling. On the other hand, when you add them together, it just happens that the resultant wave seems to be staying at their location. Each point seems to be not moving to the left or the right. They seem to be just moving up and down about their own location. And of course, each point seems to have a different displacement magnitude. Maximum displacement occurs at some points we call anti-nodes. Now, these points labeled as A, they are called the anti-nodes, where you expect the maximum displacement of the particles. And there are locations in the standing wave where you see no displacement or no displacement at all when the wave is oscillating. So they are called the nodes, where you will see no displacement of the particles. And that is what I mean. We are actually seeing what we call a stationary wave. But the result of the stationary wave is due to the superposition of two traveling waves. So that is the important message at here. Standing wave is a phenomenon that arises from traveling waves. And the characteristic of the traveling waves is that they are having the same, typically they are having the same frequency. Typically they have the same frequency and comparable magnitude. Otherwise, they would not cancel each other. So if they have the same frequency and same magnitude, they could completely cancel one another from time to time. And they are traveling in a certain sense in the opposite directions. So that is why you could see in the simulation, two waves traveling in opposite sense, in opposite directions, and to generate a standing wave. And in the standing wave, you could see positions where there are maximum displacement. These points for maximum displacement, they are called the anti-nodes. And there are also positions where there would be no displacement at all over all the time. And they are the locations of the nodes. So in your lecture notes page 60, you see the name anti-note and the note. So the standing wave is due to the superposition of two identical waves with the same frequency, same amplitude, traveling in opposite directions. And the amplitude of the standing wave, as you will see, say, let's pause it now. The amplitude of this standing wave, you could see that, okay. So it is having a magnitude that doubles that of the incident waves. The magnitude of the standing wave is doubling that of the incident wave. And there are some other points that we could see in this simulation. For example, what is the distance between two nodes or two anti-nodes? What is the distance between adjacent nodes or adjacent anti-nodes? This here, from this node to this node, it is half of a wavelength. Similarly, from this antinode to this antinode, it is half of the wavelength. So the distance between two nodes would be half a wavelength, and the distance between two antinodes would be half of a wavelength. And this is the characteristic of the standing wave. If you're interested, I could just copy the, you see, I could just copy the link on the Zoom so that you could take a look by yourself later after, during the lesson. Right. Okay. Now let's come back to the lecture slide. So this is the standing wave pattern. I should be sharing the screen, I believe. Can you see it? Am I sharing the PowerPoint slide? No, okay, just a minute. Okay. Right, that should be now. Right, so at here, we come back to the lecture notes. At here, this is some more verbal descriptions on the standing wave pattern. When you have the two waves, two traveling waves that are moving towards one another, due to the superposition, then there would be standing wave generated on the string. Now, please note that standing wave generation need to meet some specific conditions. Firstly, we have to remember that the nodes and the antinodes, they are separated by the distance of lambda over 2, meaning that the distance between two antinodes or the distance between two adjacent nodes. Oh, sorry, I should do it like that. These are the locations of the antinodes, A, A, where you expect the maximum possible displacement. The distance between adjacent antinodes, it is lambda over 2. And the distance between adjacent nodes, it is also lambda over 2. And the distance between one node and the adjacent antinode would be lambda over 4. Now, in order to have a standing wave, there are certain occasions in which you have a node, and certain occasions you will have the antinode. This would put some restrictions on what is the wavelength that could produce a standing wave in a system. Because if the wavelength is not matching the condition mentioned here, namely that if the system does not allow the antinodes to be separated by lambda over 2 and the nodes to be separated by lambda over 2, then you will not have a standing wave. Standing wave could only occur when the distance between antinodes is lambda over 2 and the distance between nodes is also lambda over 2. How does it happen? Now, let us take a look at the standing wave on a string. Now, this is, of course, just a simple string, and there would be certainly some tension that could be generated on a string. And when you shake the string, it typically would introduce a lot of different frequencies of oscillation in the string. But only the suitable oscillations which would support the nodes and antinodes in specific locations, then we could have a standing wave pattern. Now, I just show you a video for demonstrating why how specific it should be in order to generate a standing wave in the vibrating string. So I will show you a video up here. This is a video on YouTube. So I just play from the beginning. Specific criteria that the nodes and antinodes are always separated by the same distance, which is lambda over 2. And you would also notice in the video that standing wave seems to occur only at specific frequencies. As you will see, n equals to 1, meaning that you have only one loop. And here you have 2 loops. You see that there are 2 loops. And here, 1, 2, and 3 loops. N equals to 3. They seem to occur at specific frequencies. What about other frequencies? You will start to wonder. In other frequencies, because they would require the nodes to be separated by, once again, lambda over 2, the length of the string cannot support it. Otherwise, you would have 2.5 knots, and that is actually not possible. We will see later why that is not possible. So only specific frequencies could be supported. For example, here n equals to 3 is 41.1, n equals to 4 is some other frequency, and so on. Now, let me see if this video will show you.
Another way to look at resonance is to look at what are called modes
n
of
must be
vibration
an integer. If it is not an integer, then it cannot support a standing wave pattern. The reason is to be explained a little bit later. So let me see if this would show you how it changes when you vary the frequency.
Behave differently. This is 10 hertz, and this is 11 hertz right here. So you can see now, we'll freeze this. The string is in what's called its first mode of vibration. This is the frequency, 11 hertz, for this particular string and this particular
there should be some other
this
videos
is the
on
frequency
YouTube which
it wants to resonate at,
gradually
the lowest
changes
one.
The frequency.
This 11 hertz, so 11 times per second. What you can see is that even though we haven't changed the amplitude, the amount that the driver, the woofer, is moving up and down, the amount that the string is moving up and down in the middle has changed dramatically.
Search it a little bit,
and that's because it wants to ring at this frequency. Let's start the video again and see what happens if we increase the frequency again. So this is 11 hertz.
Okay, let me see if it is this one.
Transverse that string. A loudspeaker string that is suspended by the driver and the pole. I'm not quite there. You can see it's trying to find it, and there it is. So that is 11 hertz here on my sine wave generator. And what we're seeing here is what's called the first resonant frequency, or the fundamental resonant frequency of this string. Now, this length of string represents one half wave. If it were a sine wave going up into that wave, that would be the next harmonic. So if I go up to 22 hertz, now we're getting 0 degrees.
And show you what happens
now that resonates.
If you have
infinite harmonics can be found on this string.
Okay, now let's jump to the lecture notes and try to see why. Now, at here, you have a string that is fixed at both ends. Remember, at the positions of the node, you have the minimal or zero displacement. And at the positions of the anti-nodes, you have the maximum displacement. Now, if you have a string that is fixed at both ends, you are forced, in a certain sense, you are forced to have a standing wave pattern where there could not be any displacement at the two ends. Now, this would already place a lot of a constraint on the acceptable frequencies of the standing wave. So that is why I said a standing wave can only be generated when you meet a certain criteria. So what would be the criteria in this case? For example, the case where you have the simplest standing wave pattern is you have two nodes at the two ends. When you have the nodes at the two ends, then you would have an anti-node in between. So that is the situation here, where you would have a standing wave pattern that supports two nodes at the end and one anti-node in the middle. Now, what is the frequency of the wave? To answer this question, let us instead ask what is the wavelength of the original wave. remember the wavelength is related to the distance between the knocks in the standing wave pattern. So the distance between the knocks here is, of course, the length of the string, but it should also be equal to half of the wavelength. So this would be the standing wave pattern that is the simplest and with the lowest frequency. Length is related to the wavelength. Length of the string is related to the wavelength, and therefore the frequency, which is equal to V over lambda, V over lambda, that would be equal to V over 2L. So it is related to the geometry of the setup. So this would be the simplest case of a standing wave, where you have, in this situation, a standing wave in a string fixed at both ends. When you fix at both ends, you are forced to have knocks at the two ends. Simplest standing wave is having one single anti-knock in the middle. You will start to wonder, can we have some other patterns of the standing wave? Yes, we can. The idea is we could put in some other knocks in the middle, just like the case of the string shaking between the two supports. So here you have another standing wave pattern. The one on the left-hand side, it is called a second harmonic, as in contrast with the previous one, which is the first harmonic, because firstly, you have the frequency of the second one, which, as we'll see later, doubles that of the first harmonic. And secondly, this would be the case where you have the next simplest scenario. In the previous scenario, there is one anti-knock. And in this scenario, you have two anti-knocks. So in between, you would expect another knock. To fit in the geometry, once again, distance between two knocks has to be equal to lambda over 2. So at here, the whole string should be equal to the wavelength, because you will have, say, at here, from here to here, it is distance between two knocks, and here to here is the distance between two knocks. So altogether, that is equal to one wavelength. The next more complicated scenario is it is supporting 3 anti-knocks. And of course, in between the anti-knocks, there would be the knock as well. What about the relation between the length and the wavelength? Between the length of the string and the wavelength. Here, distance is lambda 3 divided by 2. Lambda 3 corresponds to the third simplest scenario. This is lambda 3 divided by 2. This is lambda 3 divided by 2. So altogether, the length of the string should be equal to 3 lambda 3 divided by 2. And you could always calculate the corresponding frequency by the equation shown here. So you have Fn, which means the nth normal mode of oscillation. And as you would see from the previous case, lambda n is basically 2L divided by n. Check it from here. Here, lambda 1 is equal to, let me see, lambda 1 is equal to 2L. here lambda 2 is equal to L, lambda 3 is equal to 2L divided by 3. Or we could write lambda 1 is 2L divided by 1, lambda 2 is 2L divided by 2, lambda 3 is 2L divided by 3. That is what we have here. So Fn is V divided by 2L over N. And we could write down the equation like this. N is integer. You cannot support non-integer standing wave pattern. And you could see that here, the term square root T over mu, which is the speed of the sound in the string, or the speed of the wave in the string, the speed of the wave in the string, this is a constant. As long as you have a constant tension and same string with the same mass per unit length. L is fixed by geometry. Therefore, N is the only variable at here. And when N changes, then the frequency changes accordingly. So you could see the frequencies for the standing waves, they are multiples of this term T square root T over mu over 2L. So that is how we could observe the standing wave of different frequencies in the string. And in the case of a string fixed at the two ends, you will see that the knocks must be occurring at the ends of the string because they are fixed. You cannot expect any movement for the particles. And any variation occurs in the middle. So if you want to have a fundamental oscillation, you have one anti-knock in the middle. If you want to have more complicated scenario, you could introduce more and more knocks in the middle of the string. Corresponding frequency of various standing wave patterns could be calculated like that. They all follow the same pattern, where Fn, as you will see, it is equal to N times F1. F1 is the frequency of the fundamental at here. Oh, sorry, at here. Fundamental at here. So the frequencies of various standing waves, they are related to one another in the case of a string fixed at two ends. Now, some of your classmates is asking, is that the same principle that is used to use in the resonance due to the length of the water column experiment? Yes, it is. And actually, in your tutorial 4, you will have one question related to that. We will see it later. Now, how is it related to our daily life? Okay, so this is just what I have described. The fundamental frequency corresponds to n equals to 1, n equals to 1, and it has the lowest frequency. And all the other natural modes would be basically multiples of the fundamental frequency. And the frequencies of the normal modes, they would form what we call the harmonic series. So you will see that the frequency F1 is the first harmonic, F2 is second harmonic, F3 is the third harmonic. And correspondingly, F2 is equal to 2 times F1, F3 is equal to 3 times F1. The scenario that we have just described is quite familiar to many of you, I believe, if you play musical instruments, for example, guitar. Because in a guitar, you have the string fixed at two ends, and you pluck the guitar string, it would generate a certain note of specific frequency. You do not expect other frequencies because other frequencies are not supported. Other standing wave patterns are not supported by the string. If with some skills, you may set up higher harmonics. You may set up higher harmonics, but nothing in between, not any random frequencies. So here, let's take a look at an example. And we are trying to generate a note of frequency of a C, which has a fundamental frequency of 262 Hertz. So if you want to find the next two harmonics, in the case of a string fixed at two ends, this is the fundamental harmonic. You usually draw a loop like this. And then you could have another harmonic, which is like that. So two loops. So the second harmonic is 2F, third harmonic 3F. So that is how you calculate the frequencies of the next two harmonics. And if you are generating the harmonics by the same string, but vary the tension in the string, if they are the same string, you expect the same linear mass density, and they have the same length. For the fundamental frequency, it would be given by the equation in full like that. So by varying the tension in the string, you could obtain a note of different frequency. So here, you are trying to adjust the tension in the string. So instead of playing a C note, which is 262 Hertz, you try to adjust it to play an A note with the frequency of 440 Hertz. So that is why you are comparing the frequencies. You have the ratio of the frequencies, which is related to the ratio of the tension square root from the equation at here. So it is just dividing F1A by F1C to obtain the equation. And the strings, as we have just seen, is actually undergoing what we call the resonance. Because during the resonance, you could observe the strings are oscillating with fairly strong amplitudes. And this would be something supported by the string system. Only when the frequency of the oscillation is matching with that of the system, then the standing wave pattern could be supported. Other frequencies are not supported at all. So this phenomenon is called the resonance. When you have an external driving force that tries to set up an oscillation in the system, the frequency of the external driving force need to match with that of the system. Otherwise, the system would just die down very quickly. If it matches with that of the system, the oscillations becomes very strong. So that is the behavior of the resonance. When it matches, when your oscillating system is at the resonant frequency, it would exhibit a very large amplitude of the oscillation. And if the system is driven at a frequency not matching with the natural frequencies, then the amplitude would be very small. In fact, one of your classmates has just already asked the question. This phenomenon is also occurring, say, in the sound wave. When you try to blow air into a glass tube, for example, you have the glass bottle, say the Coca-Cola bottle at home, you try to blow air into the Coca-Cola bottle, you blow it randomly, and it would always give you the same note, the notes of the same frequency. It is because only the driving disturbance of the matching frequency can set up resonance, can set up the standing wave. If it does not match with the standing wave condition, then it has a very weak amplitude. So it does not generate a very loud note. Only when it matches the resonant frequency, it will generate a very loud note. So that is the next topic we are going to look at, which is the standing wave pattern in the air columns. Okay, I would take a break about 5 minutes, and then I will try to do the explanation in the next, after the break, about the standing wave in the air columns. At the meanwhile, maybe I could show you some videos. So I may first show this one.
Controlling the frequencies in tubes like these is the basis for several musical instruments, including the pipe organ and the woodwinds.
Not sure if you could hear the sound. Seems that I cannot. Okay. You may have to tune on the sound by yourself.
Take a bottle or a tube or a cylinder and blow air over the top. It will resonate, and from this you can measure the wavelength of sound. And if you know the frequency, you can also measure the speed of sound. But why does blowing air over the top of a tube or a bottle cause it to vibrate? Try this. Take 2 pieces of paper and blow air between them. The pages flutter in the turbulence, and when you blow air over the top of a bottle or a tube, it also causes a turbulence. The open end of a tube is a place where the air is free to move in and out, an antinode. The bottom of the tube is a place where the air cannot move, a node, a location of node displacement. When it comes to waves, the wavelength is usually measured as the crest-to-crest distance, but this device only gives us a node to antinode distance. That's only 1/4 of the whole length of the wave. Therefore, 1/4 of the wavelength is equal to the length of the tube. Since this cylinder is 25 centimeters long, we know that the sound we are hearing has a wavelength of 100 centimeters, or 1 meter. Now, at room temperature, sound waves travel at 340 meters per second. And if the wavelength is really 1 meter, then the sound waves we are hearing have a frequency of 340 hertz. You can verify this on an oscilloscope. Or, if you have a 341.3 hertz F tuning fork, it will resonate when held vibrating over the tube. Hey, a perfect match. Well, pretty close. What if you don't own a 341 hertz tuning fork? Well, then you can add water to a tube to adjust its length. Here's another trick you can try to instead measure the speed of sound. Take a tube that's open at both ends and dip it in water. Then with another tuning fork of known frequency, try to find the resonance. One-fourth the wavelength seems to be about 29 centimeters. That makes the full wave about 116 centimeters. By v equals lambda f, velocity equals wavelength times frequency.
Yes, it is always n times the fundamental frequency, and n needs to be an integer. N has to be an integer.
What about double open tubes?
As you will see in many of the deviations, you are supporting multiples of the standing wave loops.
But between any pair of
you cannot support random number of the loops that is not an integer.
In fact, the wavelength is twice the tube length. These tubes will resonate too, and once again you can measure the wavelength and the speed of sound. Now here's one more piece of the puzzle. The higher harmonics. The lowest frequency that fits in the tube is called the fundamental vibration, and its wavelength is 4 times the length of the tube. The next highest vibration is the third harmonic, not the second harmonic, but 3 times because of asymmetry reasons. The next highest one is also an odd harmonic, the 5th harmonic, who does fit 1 wave in the tube and a little bit more, and its frequency is yet even higher. In the case of double open tubes, the symmetry allows for all integer multiples of the fundamental to resonate, not just the odd ones. However, the fundamental wavelength is now twice as long. Now it's time for a puzzle. If I cover the open end of this tube, how will that change the note that resonates? This little window is a place where the air can move freely in and out, an antinode. And so is the other open end of the tube, also an antinode. So the wavelength that fits in is twice the length of the tube. But if I cover the open end, I now have an antinode node situation, and the wavelength that fits in there is now 4 times the length of the tube, which should sound lower in frequency. But will it sound lower? Yes. Cut.
Okay, just a good timing for us to come back to the lesson. And I think he actually has done some job for me in explaining the lecture notes, so I could spend a little bit less time on that. The idea is that in the just before the break, we introduced the standing wave pattern generated in a string that is fixed at both ends. And in that scenario, because the 2 ends are fixed, we cannot have any particle vibration in the string at the fixed end. So we are forced to have knocks at there. And in the video demonstration that we have just seen, we are talking about the standing wave pattern generated in the air columns. Of course, that involves the displacement of the air particles. Larger displacement of the air particles means a stronger sound, basically. So it refers to the louder sound of specific frequencies, if you like. Now, how do you generate a standing wave in an air column? There are various ways to do so. And of course, you could generate a standing wave by using a tuning fork, which would generate the standing wave of would generate the standing wave that has the frequency of the tuning fork. If the air column supports standing wave of that frequency, then it is displaying a loud sound, as the video shows. If it does not match with the some specific frequencies of the air column, then no sound is heard at all. Or the other way is you try to blow air into the air column. When you blow the air, you are not introducing one particular frequency, but basically all different frequencies are possible. So when you blow the air into the air column, it depends on what is the resonant frequency of the air column, what is the standing wave frequency for that air column, and it would give you back the particular frequency that corresponds to the air column. So now we try to find out what is the relation between the frequency of the resonant frequency of the standing wave in the air column and the length of the air column. So there are two specific scenarios. One is the air column that have both ends closed. Well, that sounds actually quite strange because you would not be able to introduce any vibrations. So that is actually not existent. So I'm joking. You may have, on the other hand, one end of the air column that is closed, but the other end is open. In that way, you could introduce some disturbance, and this would allow the buildup of the standing wave. So you could have a air column that is due to one end open to air and the other end that is closed. On the other hand, you might have another scenario where you have both ends open to air, and this would still generate a standing wave. Now, you may recall at the beginning of this lesson that standing wave is generated because of the wave traveling in opposite directions. Of course, in the string, you set up an oscillation in one end, it travels from, say, left to right. Then the reflected wave would be traveling from right to left. That is okay. What about an air column that is open at both ends? Now, this is, of course, a very deep question, and it requires some good understanding of acoustics. In fact, when the air movement, if it is initially in a narrow tube and it suddenly goes to an open area, some of them could still be reflected. That is related to specific property of the air transmission in different geometries. So this is something in higher level acoustics, and we are not going to discuss it in details. But in any case, when the sound is about to leave the tube, part of them could still be reflected. And this would support the reflecting wave. So you have the disturbance generated from one side, you have the disturbance generated from one side, sending from one side to the other open end. Part of the wave will still be reflected, and it superimposed with the incoming wave. So that is why you have a standing wave generated in the tube open at both ends. Now, let us go to the case when you have the tube that is open at both ends. And the simple consideration would be that at the open ends, if it is really supporting a standing wave pattern, it should have the maximum possible displacement of the air particles. So in a case of maximum displacement of air particles at both ends, it would refer to the case of an anti-NOx at both ends. Particles should be allowed with the maximum displacement at the open end. The simplest scenario would be that you have anti-NOx at both ends and one NOx in the middle. Now you cannot have all the NOx and no, well, all the anti-NOx over the tube and no NOx in the middle. Otherwise, it just has zero frequency. So you must have a NOx in the middle. And this would be the fundamental frequency. And when you have this fundamental oscillation, the length of the tube would then be related to the wavelength of the standing wave. Because you have anti-NOx at both ends, the distance between the anti-NOx would be lambda over 2, of course, and that is equal to the length of the tube. Therefore, the corresponding fundamental frequency would be equal to V over lambda, and it is equal to V over 2L. That is for the fundamental or the first harmonic. And that is a simplest scenario. What about the next simplest scenario? The next simplest scenario is to have two NOx in the middle of the tube. In order to have two NOx in the middle of the tube and support a standing wave, once again, distance between NOx and anti-NOx, adjacent NOx and anti-NOx is lambda over 4, and distance between adjacent NOx would be lambda over 2. Here, you have anti-NOx at the end, right in the middle, and at the other end. So it is the length of the tube, it is supporting the whole wavelength. Well, I have just explained that some of your classmates is asking about the wave coming in the opposite direction. I just explained before we start that part of the sound energy would actually be reflected from the open end due to the geometry of the tube. So it is in the higher level acoustics, and that is not something we can cover at here, but the reflection does exist. And well, we could certainly put evidence of that reflection of the wave by the observation of the standing wave. So yes, that is a point, and unfortunately, that is a point beyond our level of study. So I'm not able to go any further into the details. If you are really interested, you could try to type in the term acoustic impedance in the Google and see if you could find relevant information about it. But as I've said, that is not the point of discussion in this level, so I'm not going into details. So for the second harmonic, the wavelength is equal to lambda, but of course it is equal to lambda, and lambda is equal to L. So F is equal to V over L. The frequency is equal to 2 times F1. And the next more more complicated scenario would be having three knocks within the tube, three knocks. So there would be anti-knocks still at the open ends. The distance from one end to the other, of course, it is equal to L, and it is equal to 1 to 3 lambda over 2, because altogether you have 2 anti-knocks in the tube and 2 anti-knocks at the open ends. So it is the whole length of the tube is equal to 3 lambda over 2. Correspondingly, F3 is equal to V over 2 L over 3. Sorry, I'll write it better. 2 L over 3. And that is equal to 3 times F1. So you have first harmonic, second harmonic, and third harmonics. Because the frequencies are all related to the fundamental frequency by n. N is an integer, where n is equal to 1, 2, 3, and so on. What about a tube that is closed at one end? Now, when the tube is closed at one end, once again, at the open end, we expect maximum particle displacement. But at the closed end, air particles cannot go through the tube, so it should be a knock. Now, in that situation, the case is slightly more complicated. In order to support a standing wave, there are, of course, various scenarios. Simplest one is to have anti-knock at the end and knock in the, well, to have an anti-knock at the open end and a knock at the closed end. The distance between the anti-knock and the knock is lambda over 4, and that is equal to L. So F1, it is equal to L over lambda 1, and that is equal to L over, sorry. I should rewrite it. F1 is equal to V over lambda 1, and that is equal to V over 4L. That is fine. Then the next more complicated scenario is, well, in the first case, we have no knock introduced into the tube. Then the next more complicated case is we introduce one knock in the tube. The knock, however, is not in the middle of the tube. It is somewhere in the tube such that the standing wave pattern is still supported. Remember the requirement. Distance between knocks is equal to lambda over 2, and distance between knock and anti-knock, it is equal to lambda over 4. These requirements has to be satisfied. So when you put the knock inside, you would automatically introduce another anti-knock. So the whole length of the tube would now be equal to what? This is lambda over 4, and this is lambda over 2. So altogether, it would be 3 lambda 2 over 4. What is the corresponding frequency? For this case, the frequency is equal to V over, well, lambda 2, and that is equal to let me see. L is equal to 3. I'm having a lesson. And that is equal to sorry, 4L 3 times V, 3 over 4L. So now you see that there is nothing in between, but the frequency is actually 3 times F1. So it is not simply second harmonic because the frequency is not 2 times the first harmonic. It is 3 times the first harmonic. It is 3 times the first harmonic. So the second simplest case would correspond to actually the third harmonic in the case of a tube open at one end and closed at the other. What about the next simplest case? Next simplest case would be having 2 knobs inside within the tube. Well, okay, you have a knob at the closed end, but there are 2 additional knobs within the tube. So how should it be considered? Once again, you have anti-knob at the open end, and there are some further anti-knobs in the middle of the tube. So altogether, the length of the tube would be equal to 5 lambda divided by 4. And actually, this would give you the frequency that is equal to 5V divided by 4L. And that is equal to 5 times F1. So you see that in this case, where there is a tube open at one end and closed at the other, the standing wave frequencies supported or resonant frequencies supported, they are in the form N times V over 4L, where N is not simply integers, but they are odd integers. They are odd integers. Well, as I just explained, you cannot have even integer modes. As you will see, I try my best already to fit in standing wave patterns, but the first standing wave pattern corresponds to n equals to 1. The next simplest standing wave patterns correspond to n equals to 3. I do not intend to skip the 2, but it does not exist, basically. The next would be n equals to 5. So this is the consequence of our deduction. N would be odd and no even modes, basically. For the case where you have a tube open at one end and closed at the other. So this is the case of the tube open at one end and closed at the other. There are some other specific points. For example, concerning the musical instrument, you have the temperature dependence of the frequency, because as the temperature increases, yeah, the second one should be the third harmonic, as in the last slide. So for the higher temperatures, it would raise the frequency of the knobs, because in many of the equations, you will see the fundamental frequency is proportional to the speed of the sound wave. So when the temperature increases, it increases the speed of the note, and the frequency increases for the air columns. But for the sound wave produced by the strings, the mechanism will be slightly different. When the string is increased in length, the tension decreases and it would reduce in a lower speed. So that is a slightly different scenario. And here we have two examples of standing wave in the air column. The first one would be a drainage culvert, basically a tube, if you like. When you blow at the open end, it would make a sound. And this is a tube which would be closed at the other due to the presence of the water. Or let me see. No, it is a drainage culvert across its open end. Sorry, across its open end. So it is actually a tube open at both ends. It is a tube open at both ends. So you try to deduce the corresponding first three harmonics. So you may use the equations provided in the lecture notes. Alternatively, what I would suggest really is to deduce the equations by yourself in the, depending on the situation. The case could be quite straightforward. If it is open at both ends, the standing wave would be something like that. Now I'm always trying to draw the loops of the standing wave pattern, where the largest amplitude corresponds to the antinote, and the meeting point where you have the minimal amplitude is the note. So the length is related to the wavelength, and therefore frequency is equal to V over lambda, and you could deduce what is the corresponding frequency in relation to the length of the tube. Next harmonic would be obtained sequentially. And if the tube is open at both ends, you could support all integer harmonics. If, however, the tube is blocked at one end, then you would only support odd harmonics. And even the fundamental frequency would be changed, because in the case where the tube is blocked at one end, it would be an antinote to one side and a note at the other side. So the fundamental frequency would be changed accordingly. And that is how we do that calculation. And the next example is similar to the one demonstrated in the video, where you have the standing wave generated in water column by means of a tuning fork. You send in a sound of a specific frequency. Only when the air column length matches with a standing wave pattern, then you would hear a loud sound. Other frequencies are not considered. So when you change the length of the air column, what you are changing is the mode of standing wave. The frequency is still the same. Wavelength is the same, but the mode of standing wave is different when you change the air column. So how does it work? when the length of the air column is very short, at the first resonance, you will support the first harmonic. So that is the case. L is equal to lambda over 4. And then when you raise the tube, the water level is lowered, it would become the next resonance. We call it the second resonance. The second resonance for a tube open at one end and closed at the other, it would be third harmonic. It would be third harmonic because at here, lambda is equal to 3, well, L is equal to 3 lambda over 4. The lambda in this case would be exactly the same because it comes from the same tuning fork. Frequency is identical. Next, L is equal to 5 lambda over 4. So you have at here, let's see, the length of the tube. The smallest value of L for the peak sound intensity to occur is 9 cm, which already gives a hint that L here is equal to 9 cm, and that is equal to lambda over 4. So you get the corresponding fundamental frequency, which could be calculated as long as you know the speed of the sound. And the next thing to do is to calculate the length of the tube at the second resonance and the third resonance. So hopefully the example would not be too difficult to understand, I hope. And in the next lesson, I will be doing some tutorial questions before we start on the lecture on lecture notes number 4. So hopefully that would help you to understand more about the standing wave. Right. So in the remaining part of the lesson, which is around 20 minutes, I would introduce another phenomenon related to the superposition of the wave, but they are not standing waves. In fact, superposition of the waves always occur when you have basically two waves meeting one another. And here, the superposition of the waves occur between two sources that have slightly different frequencies. So this would be generating a very odd phenomenon where when you play the two sounds of different frequencies together, sometimes they would generate a constructive interference, but as time develops, they would generate destructive interference. The situation is like this. The two waves have slightly different frequencies. So you have the blue and the green waves. At some point, like at here, the waves are in destructive interference. So x-axis is time, y-axis is the displacement. At other points, like at here, the waves are in phase. They are moving up and down in the same manner. So you expect a large pattern. So what does that mean? If you really add them together, graphically, you will see something like in the figure B. At some point, the two waves are canceling one another. So you expect zero amplitude. At other points, the amplitude would be much, much larger. So what happens is that amplitude of oscillation is not just dependent on the wave itself, but it depends on the time. And this would create a fluctuation of the amplitude, which, if it is the case of the sound, it would create a fluctuation of the sound loudness or intensity, which I could show you at here. So this is a simulation from a university, which I could post it for you. So here you would have, let me see, two sounds that are different by 1 Hertz. Two sounds that are different by 1 Hertz. And what happens if you listen to it? I'm not sure if you can hear anything. Don't think you could hear anything. Let's try again. Oh, you could hear. Okay, that would be good. I cannot. I'm sorry. Let me see if I could find it myself. Okay. Right. What I believe you are hearing is a variation of the loudness of the sound. And the frequency should be around 1 Hertz, meaning that the loudness goes up and down every single second. If the frequency between the two sounds are varying, what you could hear is changing frequencies for the loudness variation. So this would be something we call the beats. Beats is referring the periodic fluctuation in the amplitude of the wave. It refers to the periodic fluctuation in the amplitude of the resultant wave, because there is a slight difference of frequencies between the two sources. So if you have, say, a frequency of one sound being 400 Hertz and the other one is 401 Hertz, you could hear the beats. And quite interestingly, the beats frequency is actually the difference of the frequencies in the two sounds. So if one is 400, the other is 401, then you have the beat frequency that is equal to F1 minus F2, which is 1 Hertz. Of course, we do not know which one is higher or which one is lower, but we are just considering the absolute difference between the two. So this is the important thing. Let me see if I could find something on the YouTube. Okay, I think this one should be working quite well.
So I'm going to demonstrate the phenomenon of perspective if the beats instrument being tuned simultaneously, the oboe and the violin or the oboe and the French horn or whatever. So I'm going to demonstrate that with these tuning forks and in a piece of weight, so that the two tuning forks come out with about the same frequency.
But one has a mass attached to it.
So when they're tuned, you can hear a nice steady tone that doesn't vary in loudness. But when you vary the frequency of one of them, even a little bit, then you get the following phenomenon. Can you hear a wah, 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 wah? Let me do it again.
Yeah. So that is the
Wah,
fluctuating,
wah, 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 wah.
fluctuating loudness.
The farther
That
these
is
are
the,
from being tuned,
phenomenon
the
of the
faster the
beats.
wah-wah pattern is. So these are even further out of tune. What I'm doing by moving this weight is lowering the frequency of this tuning fork, and the other one is staying the same. And you should be able to hear wah, 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 wah really fast.
Now, of course,
And
if the frequency difference between the two sources are very large, then the oscillation in the loudness would be very quick, meaning that you might at one point unable to determine the whether the intensity is varying or not if the difference is really too large. But if the difference is very small, then you could hear it. And that is actually a trick used by the technician who tune the musical instruments. For example, if they want to tune the piano, they would take a tuning fork that has an accurate frequency for the note. And he would, at the same time, struck the tuning fork and place it near the piano. And if he hit the piano key, and if he hears the beats, that means the piano is out of tune. So he has to adjust the piano accordingly. So that is the phenomenon of the beats. Now, let's again try to go back to the lecture notes. So as I mentioned, this is the case of the tuning piano. You have two piano strings, and each should be tuned to 440 hertz. And then the tension of one is increased by 1%. So the idea of the piano generating sound is that they actually have strings that are fixed at both ends. You have the strings of the piano that are fixed at both ends, and you try to tap on the string in order to generate a sound. So the frequency of the sound is related to the length of the piano string, so V over 2L. And the speed of the sound, as you will see, is related to the frequency of the sound. The speed of the sound in the string is given by square root T over mu. So the frequency is related to the square root of the tension. By making this consideration, you could see what is the relation between the frequencies and the tension. And then if one of the string is tightened by 10%, by 1% in tension, then it would generate a different frequency compared with the original string. So the difference in the frequency would be corresponding to the bit frequency. So that is the idea of the bits generation in if you have the two sounds that comes next to each other and they have similar frequencies. The deviation of the bits frequency it is not included in the lecture notes. But for those who are really curious, either you could go to the free textbook for the deviation, or many of the internet sources would have the deviation. The mathematics, it is just the addition of sine or cosine function. So in principle, they are not really difficult. The main difficult part is that you have to identify two functions. The first is the oscillating function in the middle, and the second one is a envelope function that would limit the amplitude of the oscillation from time to time. So if you really go into the details of the deviation, you would be able to understand how the intensity varies and what is the final frequency of the oscillation in relation to the initial frequencies. So that is the idea of the bits. And here we would just be using this equation as a result to do our calculation. So as I said, I'm not going in into the tutorial today because we have only around 8 minutes left, and we would be doing it in the next Tuesday. But before the end of the class, let me just try to come back to the Learn at PolyU for some quick announcements. Once again, I have posted an announcement on the Learn at PolyU asking you to declare your current location. It is related to the examination venue. So PolyU has announced some time ago, in September actually, that some of the courses would be having invigilated examination, meaning that students have to come back to campus to take the examination in the exam hall. However, for students who are currently not in Hong Kong, we would make arrangements for them. The exact arrangements, how to do the invigilated examination online, would be announced later. Well, it is not a simple process, but we have to do it. We have to do it. So if you are not in Hong Kong right now, you have to declare the situation by completing the form in this link, by completing the form in the link on Learn at PolyU. So here, by clicking at the link, you would fill in a very, very simple survey form. You just have to tell us whether you are in Hong Kong or outside Hong Kong at the moment. We may ask you for proof. We may ask you for proof. The deadline should be yesterday, but in case you have not done so, please tell me, and I would try to take your response once again. If you are not responding at all, I would assume that you are in Hong Kong and you would have to come to examination. You would not be given a second chance to take the exam if you are not in Hong Kong but have not declared. You have been asked to do so already. So that is the important message. And we also have the assignment 3.1 and 3.2 that is ongoing. Well, if you are not in Hong Kong, we may ask you for example, tickets or some other documents. We would send out emails to ask you for the proof individually. So we will talk about it when you are asked to do so. So for assignments 3.1 and 3.2, some of the classmates have experienced problems in question 1 of assignment 3.1. And I have sent an announcement on a Learn Poly U saying that for this particular question, please take A with 1 significant figure and K and omega with 3 significant figures. That is an unfortunate situation due to the stupidity of the computer. The computer can only take in specific patterns of the numbers. If it is not that pattern, it does not recognize it as the correct answer. So it is too late to teach the computer right now because some of the classmates have already done the question. We would try to take a look at the answers after the assignment is over. So if you have got it wrong and you have finished all the attempts, don't worry. We would take care of it. Some of your classmates have gone in details asking what is the optimal number of significant figures in the final answers. Never use decimal points as the criteria. Consider significant figures. It is more meaningful to provide us with 3 or 4 significant figures rather than following a strict answer of 1 decimal point. If the answer turns out to be 0.005 and you use 1 decimal point, it will become 0. That is not good. So significant figures would be more meaningful for discussion. Typically, for a meaningful answer, it would be 3 to 4 significant figures. In the calculations, you keep more, but as the answer, you use 3 to 4 significant figures. Do not copy and paste the calculator answer, which has usually 12 significant figures. That is meaningless because the measurements are never that accurate. So you give us 12 significant figures, it is just meaningless numbers at the back. And if we are talking about real engineering or scientists, we would not try to do that. Once again, computers are not that smart yet. So it cannot handle significant figures easily sometimes. So it may be, there may be some complications. If you encounter any problem, email me and we will try to sort it out and announce it to all the classmates. Okay. So I think I would have to stop it here. Yeah, TensorFlow is something not related to the course, but that would be the trend of the future engineers. So if you do not know what TensorFlow is, go and have a look. And this is the trend of the future, really. Artificial intelligence. Well, not included in my course. So with that, I would have to stop the class, and we should be seeing again next Monday. Okay, thank you very much.